He's a professor at the University of Southern California Electrical and Computer Engineering Department. Before joining USC, I think he was at Intel for a long duration. He got his PhD from University of Michigan, Ann Arbor. Here he is holding a visiting chair professor position, and he'll be with us for a year. And he will be teaching a course next semester. He has already interacted with students in the computer architecture course, and we hope to have a lot more interactions very quickly.
Good morning, folks. I have a lot of slides, but we could just cover 5 slides and be done with them all hours. So please interact. If you have questions, stop me. And I know some of you are taking my class, so you know my style. One slide, half an hour. So it's my pleasure to be here, and it's a great opportunity to actually present some of the work that we have been doing in my group at USC. But I hopefully going forward with some of you who are particularly interested in hardware and machine learning interactions. And so with that brief introduction myself, this is going to be focusing on private and trusted machine learning. And in particular, what I'm going to focus on, and I'm going to give a series of talks actually over the next couple of months, just as a preview. So if you're not bored by this talk, the second talk would be on multi-party computing, where we're going to talk about how MPC can be implemented more efficiently on existing hardware. So, but that's a preview. But here we're going to talk about how we can use trusted hardware, in particular Intel secure enclaves, to improve the performance of private machine learning. That's the focus of it. Okay, so we know that deep learning has many applications in our daily lives, from essentially manufacturing, healthcare, and transportation. Every field we actually live in today is touched by machine learning in one way or the other. That's not something that is debatable at this point in time. And the problem with machine learning is that other than the few people in this room, vast majority of the people outside of the campus have no clue what machine learning is. Particularly, they all heard the word, they all want to use it, but they are not experts in the machine learning domain. And that means the companies that are going to try to make it very simple for people to deploy the machine learning algorithms in whatever workflows that people may have, in a transportation business or in other secure healthcare industries and so on. And so the machine learning as a service is going to become a very popular system. So basically what it means is that you have some kind of a cloud service provider, let's say an Amazon Web Services or Google or Microsoft, any of these companies. And they will provide you some kind of a model and give you a set of APIs. And all you need to do is to code into that API, and then your model is being trained using your own data in their cloud. So the model is in the cloud, your data is with you, and you just use this training API and the prediction API, and then you can get sort of benefits of all the millions and millions of dollars of research that is being spent on machine learning. You get immediate access to it in the cloud. So it seems like a very interesting and appealing programming paradigm, because people already are used to using the cloud. And all you need to do is to put up a few APIs, and suddenly the ML models are now integrated into your workflows. So that's basically what people have been working on. And so, in fact, practically every cloud provider actually has this API that you can actually use in today's context. And so, and there's also other reasons. Apart from being a novice to the machine learning algorithmic models, you may also not have access to 64 GPUs sitting in your basement, right? I mean, it's not easy and it's very expensive. So if you just want to get a slice of the GPU for a few hours in a day, that is a much cheaper option also. And so given this paradigm, yes?
Question that if the model fixed, or can the client change the model also? So what is the neural network, underlying neural network?
So the model that is, so the model can be changed. Like you can choose, let's say, a object detection model which detects objects in a floating
Just say the number of
usually, how much of an architecture that you want to specify depends on how much of a prowess you have in the domain. Because for most people, they don't want to know how many layers, or they don't even understand what a layer is. Like you click a button on input and output comes with the prediction, and that's all they care for. And hence we make the assumption that you pick any model that you want. If you want to specify a specific number of layers, that's all up to you. but we don't really have a restriction in what we present in this work. There is some model F that is selected by the users. It could be selected by some cloud entity itself, or any of those combinations. It doesn't really matter for our work. Yeah.
The training setting, are batches of data sent from the user to the cloud, then they are trained?
Yeah, so I'll talk about it. If we get to the second half of my talk today, there is a federated learning model where the users actually hold the data. Let's say that you have some medical images that are private and you don't want to share with the cloud directly. You actually can sort of encrypt the data and send it to the cloud to do the training in some sense. And so there are different paradigms that we can actually consider in this system.
So you're considering both the inference as well as training?
So in fact, the work that I'm going to talk about the first half is actually applicable both to inference and training, but training is a bit more complicated. And so for the purposes of sort of dissemination of the work, I'm actually going to focus on inference, but the applicability is also in the paper. We actually showed how it can be done for training as well. And so here is a simple, what we call outsourced machine learning paradigm. So you have some deep neural networks, the multiple layers, and all the standard stuff that you know. And users have a data that you want to do an inference or train on, and they send that information to the cloud service. And the cloud service runs the application through the input through the DNN layer, and then it provides the prediction back to the user. It's relatively straightforward and makes life easy. Everybody can use it, and it kind of democratizes the process of machine learning in itself. So it seems like this is a great model. We are in a happy world, and why change anything in this? Here is the problem. If we are going to trust something to the cloud, can we really trust the cloud to trust our data? In other words, if you are going to send the data, how do you know that the cloud is not keeping a sample of your data in its own data sets, for example? How do you know that it is not malicious? And maybe you trust Google's or Amazon's because they have a lot of liability issues. But how do you know that even these Google's and Amazon's are not hacked? A particular subset of computer systems may be hacked. And hence, the trustworthiness of the cloud service itself is a big question mark in many, many ways. I mean, there are, the history is littered with the security holes that exist in cloud computing paradigm. And hence, we can't just simply say, I can send this stuff to the cloud and I can close my eyes to the security consequences of this particular paradigm. And so this is a serious problem, and somebody has to work towards the solution. And so the data privacy, computational integrity, these are the two challenges. Computational integrity means privacy, you all know, right? I mean, like if I give you the data, if I give the data, only the people who are given the data should have access and nobody else. That's the privacy. And then the computational integrity means when the CPU or the GPU in the cloud actually performs some computations, how do you know that if it is at 2 plus 3 equals to 4, how do you know that it is actually done 2 plus 3 equals to 4 as opposed to 5? And hence you want to also verify that the computation is done by the cloud is actually correct. And so you have these two sort of compelling tension between I want to do something in the cloud, I don't trust it. And I don't know if the results that I get is also correct. So with all of these constraints in mind, we have to have a solution that works across all of these spaces. And so obviously you will say, why are these challenges occurring? Well, there are lots of attacks, right? Operating system level attacks, hardware and physical attacks, and other application level attacks. And of course, more fundamentally, the legislation is coming to you, right? GPDR, the GPDR, HIPAA, and Consumer Protection Acts, these are going to force on the companies that when I give you the data, you can just use it in whichever way you want. And so there are lots of actual economic and business environments that are going to force you to tackle these problems in practice going forward. So given this environment, where do we go from here? Where we can go from here is in multiple dimensions. We can go from here to fully homomorphic encryption. For those of you who are familiar with homomorphic encryption strategies, you can compute directly on encrypted data. Very expensive today, but it's a possibility. MPC, multi-party computing. So I know some of you actually work extensively in this department on multi-party computing, and so multi-party computing solutions can also work. And then trusted execution environment. This is the hardware coming to your help, and how can hardware help you? And so in this part of the talk, I'm going to focus on the trusted execution environments. And as I said in the preview, in the next seminar I'm going to give you, we will be focusing on the MPC paradigm of this. So let's take a look at what TEE means. A trusted execution environment, or also called a secure enclave, is a computational model that is actually given by certain kinds of CPUs. For example, Intel's certain class of CPUs from Intel provide this enclave execution environment. And similarly, ARM uses something called trust zone, if you're familiar with ARM architecture. And so different kinds of computing systems, or ISAs, have different kinds of models, but they all kind of sort of put a bigger umbrella under it. Trusted execution is executed through a secure enclave. What does that mean? A secure enclave, for example, here is my processor. I can create a small virtual machine. Think of it as, for simplicity's sake, think of it as a virtual machine where you can run your code within that virtual environment. And within that virtual environment, when you run the code and the data is protected, not only it is protected from some potential hackers, it is also protected from the root user on the computer itself. So for example, this is my laptop and I have, I own the machine and therefore I have root access to it. But if you run an enclave on my machine, I can't actually see what you are performing on that enclave. I can kill your application, but I can't see the data or the instructions that are executed inside this enclave or trusted execution environment. So this is something that is provided extensively by Intel. Basically, you can say that this is my data that needs to be protected. This is my application module that needs to be protected. And then you can basically have an application that is signed, the data that is sensitive is actually encrypted, and then the world becomes sort of within this enclave, everything is protected in that sense. So, for those of you who are really familiar with enclave, you can come back and say, look, enclaves also have some issues, which is true. Side channel attacks, for example, you can see, without seeing what is inside, you can see some side information and you can still extract some private information. But for now, we are not going that far down. We say, look, it's all right. We can assume that enclaves are trusted for most parts of what we want to touch. That's the assumption that we have. Everybody following with me? All right. And so the data that is stored in the memory is encrypted, and the memory is not accessible to any code outside of the enclave, including the operating system, the root users, none of it. That's what enclaves do. And it's a whole, if you take my next semester's class, again, plug in here, we are going to talk a little bit about the enclave execution model and how that can be used for machine learning. And there I'm going to cover a little bit more details of the enclave execution itself and how it can protect it using Merkle trees and all kinds of other fancy stuff. Okay, so the problem is, okay, so now you can take your entire DNN, put it inside the enclave, and then you say everybody is off the mark, like off the limits to this enclave. Nobody can see what goes into the enclave. Nobody can see what computation is performed in the enclave. Nobody can see what the data that's coming out of the enclave, right? So that seems like a reasonably good way to protect yourself if you put your entire DNN model in the cloud inside an enclave. That will be easy, but it's not, because of two reasons. One, users, the performance overhead of using trusted enclaves is substantial even today. And there are many reasons. One of the fundamental reasons, until very recently, Intel just changed their enclave model maybe about a year ago, I think. When we started this work maybe 5 years ago, enclaves have limited memory. If you have an application that needs more than 128 megabytes of memory, enclaves are not useful. Enclaves are very slow. Extreme. It's not very slow. And the reason is 128 megabytes of memory is actually hardware protected. Anything over 128 megabytes of memory explicitly gets encrypted, stored in external DRAM, and anytime you touch that memory, you have to bring it in, decrypt it, do a Merkle tree verification, and then only you can use the data. And hence, if your model, including all the internal state, exceeds 128 megabytes, the enclaves become very, very slow to execute your model. And as a result, other than the very small basic models, as you all know, most of the models today are way, way bigger than 128 megabytes. And particularly if you consider the internal states that are actually going to explode in size, the 128 megabytes is not going to give you very much. And hence, the limitations on performance are substantial. So if you want to use your enclave to get your protection, it's very slow.
One person says that we want the entire data to be only the enclave memory, or do you decide that some part of the data which is quote unquote insensitive could be outside of the enclave, and that's why it could. For example, the weights of the model, right? They are anyway, as far as the user is concerned, the client is concerned, it is not sensitive for them. So they could say that all the weights can be elsewhere. Only activation needs to be in the.
Yeah, so even if you consider your model weights are public, which is one of the execution models, the problem is once you start putting your inputs through and then you do your matrix multiplication, you get an activation. That activation map is actually bigger than your matrix itself, and that needs to be protected. Otherwise, you can reverse engineer and find out what the input actually that went into this. And as a result, even if your model is private, which is not a big issue, your internal state that actually needs to be protected still grows substantially beyond the 128 megabytes. Maybe it will sort of move the needle farther a little bit, but not sufficient to run most of the models. So for example, today's most complex transformer models and things are into the hundreds of gigabytes, right? I mean, we're in orders of magnitude in a completely different plane altogether.
But it is possible that you could have some data outside the enclave. From a security point of view.
Yeah. I mean, it's possible, but the problem is most users, as I mentioned, I am not expecting the users who are worried about the enclave, who are going to use these enclaves and API-based models are not IISc PhD students, right? These are people who are average off the street, and I don't mean it to be in a negative sense. I mean, it's just, they have other things to do in their life rather than to read MPC book, right? It's not their life. They have things to do in terms of business models. And so I'm assuming that this is not their daily life, and therefore they just want to minimize their headache and tick off and say GPDR satisfied, right? Like you see when you go to the web page and it says cookies allowed, accept or not accept, most people will click accept, right? Because they don't want to go through the n number of 8-point font that will read the details. And so that's the same issue here. So we assume that you want to protect it and you want to be clean and clear about it. And if you want to be very specific, I want to save this privately and this is public, it's possible. Everybody with me, folks? So the problem is this has become very, very expensive to compute. And the observation is for most of the machine learning models, particularly related to vision models like DNNs and all of them, linear operations are the most of the computations are in the linear operations. What is linear operations? Matrix logic, like matrix multiplication, matrix multiplication. That becomes most of your compute. There are some nonlinear operations such as values and other kinds of softmax operations, but they tend to be relatively small and they're only in between some specific sublayers that you are actually going to perform these computations. And hence, these linear operations are really the dominating compute factor in most of these machine learning models. And we look at the compute available in the cloud. Let me say that. So before I go to that, so basically what we want to do is you want to use the TEEs, but we want to repurpose the trusted execution environments for protecting the privacy by performing, and this is the key, minimal amount of computations within the trusted execution environment, so you're not totally blocked. We're going to obfuscate the data inside the TEE. You bring the data into the TEE, you obfuscate it. Obfuscate it basically, like, and when I mean obfuscating it is in a cryptographically guaranteed manner, and therefore you can't actually say anything about the input data from the obfuscated data. And then here's what we're going to do. Because most of the computations are linear, we perform the linear computations on the obfuscated data on giant GPUs, whether they be your NVIDIA's or AMD GPUs, whatever you want to use. And then when the data is the computations are performed in the obfuscated data in the GPUs, you return the results back to the TEE, but the TEE has obfuscated the data in an intelligent manner so that it can read, extract information associated with the original data. So that's the goal, right? That's what we want to do. And so it seems like I'm not exactly sure where this is going, and so it's totally understandable. So what I'm going to do is I'm going to give you some examples of how this is actually done in the work that we are going to present. But before I give you the more mathematically solid and complex work, I'm going to give you a very intuition on how simpler things can be done. And so I'm going to start with what is called origami. Origami is the work that was published, I forget, a couple of years ago with my student Krishna. And so this is a simple empirical based solution. And it is really, really simple. And so the way it is really simple is the following. Remember the picture that I showed you where the DNN is inside the cloud? And what we're going to do is we're going to split the DNN into two pieces. There's a small piece of the DNN, the original first say n layers, that are going to be enclaved, which is basically, let's say, the first 3 layers, 4 layers, or 5 layers. And then the rest of it will be executed directly on the GPUs. Right? So you have this large computation, you slice it, how part of it runs in the enclave, the rest of it is now executed on the GPUs. The intuition behind this particular approach is that any input that goes into this model is secure because it goes into the enclave. Any input that goes into the enclave is secure. The data that comes out of the enclave is now private, is now public, but it has gone through multiple transformations, whether it be weight multiplications, values, nonlinearities, and other kinds of things. And therefore, the activation maps that come out at the end of, let's say, layer 2, layer 3, layer 4, are going to be increasingly disconnected from the input. Right? The mutual information between the input and what you see at the intermediate layers is going to become increasingly small. That's the intuition, and it's a very simple, basic approach to assume that we only run a small amount of compute in the enclave because this is all the enclave can support. How many layers do you support? Well, it depends on what the enclave supports. If the enclave is supporting 256 megabytes, we will have some number of layers. If enclave supports only 128 megabytes, we will only do half the number of layers. And the basic principle again here is that it's a trade-off. Like more you can support on the enclave, the more I can obfuscate. And so, if you do that approach, yes.
Here, what you are doing that converting the input to some form such that attacks could not be occur on.
The mutual information that is visible to the external entity, attacker, is now reduced with respect to the input that is actually provided.
In case of raw data, you are using weights that cannot figure out as you are doing calculus.
Yeah, so what happens is the input goes in, you have the weights, it gets multiplied, the input gets multiplied with the weights, and you get this activation maps. So the activation maps have some, obviously it's not zero input information, there is some information about the input, but the hope is that exactly. Exactly, that's the problem, right? I mean, empirically, it cannot provide any kind of security guarantee. For those of you who are theoretically oriented, say, well, this is not, I'm not sure how much. So the only empirical guarantee you can say is that what is the mutual information between the input and the application and the activation maps, and that is the information leakage that occurs in these systems. That's really what we can say at best. Go ahead, Prof. Yeah, so yeah, in fact, it turns out that GPDR and some of the legislations actually say that they don't expect you to have zero leakage. They expect you to have, if you're familiar with something like, say, differential privacy, they have a certain epsilon requirement that say that this has to have that kind of an epsilon requirement. And therefore, GPDR doesn't expect you to have cryptographically zero information leakage. And so there is a possibility of you connecting it back to some of the legislation based on the fact that they're not expecting a zero leakage.
How do you split it? Because you can put one part and you think that it is more to be done in the secure part. So there is some criteria to split again.
That's why I said this criteria is very like mentally not taxing, which is really simple, which is I pick as many layers as we fit into the trusted execution enclave, and that's what I'm going to do. Right? That's the approach. No, please. That's the whole reason I'm here.
Okay. State of the art ML models, like the data sets are often the ones that are in the beginning. So what is so how scalable is the
So valid. And so the thing about this is that there are certain kinds of model architectures that are more easily lend themselves to this kind of a design, right? Because this work was done around 5 years ago when Rusted 152 was the best CNN that you could have. And so it is certainly true that there's a lot of weights in the initial layers of the machine, but there's also a lot of information at the back, at the very end is the fully connected MLP layers, right? So there's a lot of computation and also the data, the weights are also in this layer. So they tend to be sort of front heavy and back end heavy and sort of lighter on the middle. So we're hoping that some of it can be kind of moved into it. Okay? All right, so it's very easy, conceptually easy to understand any of you can do it as a project. Maybe next semester, the archive, we should give it as a project and say, do this in a TEE. You get a good chance to explore how TEEs work, and you can see what the information leakage is. Here is the output to kind of give you visually. This is the inputs that are sent in a batch. At the end of layer 7 in your ResNet, this is the outputs that you see, or the activation maps that you see are at the end of layer 7. So this is, again, it doesn't give you any kind of theoretical comfort, but it will give you visual comfort and says, oh yeah, there is no information in the output that I can say that this is associated with a particular animal in the pictures that are corresponding to the input. Everybody with me? Yeah. Okay, so this is easy, and so are there people asking questions too?
No, I've been following.
Ah, okay. Okay, good. And so what is the cost of this system? So if you execute everything in the GPU, this is my baseline. This is the best system, no privacy. You get 1. That's my baseline. If you want to execute everything inside the enclave, it's 112x slower for a variety of reasons. First of all, you remove the GPU and you put a CPU in, and that's a big slowdown. And in addition, the TEE places additional restrictions on your model, and so you get 112x slowdown. So when I always tell people, privacy is not free. It has a cost, right? And that's the reason why people can sell you a data, because there's cost associated with it. And so that's 112x. And now, if I split on the 6th layer, which is this approach, which is about 43x or so. And so you can see roughly there is a substantial reduction on just splitting on the 6th layer constantly. And then origami, which is basically what I did not say is that origami dynamically selects which layer to select based on how much mutual information loss actually exists. We are trying to maximize the mutual. So the way the problem is formulated is maximize the mutual information loss for a given amount of memory that you have. That's the goal that we did on that particular origami. So if I approach that problem, you will get approximately 8x slowdown compared to GPU only execution. So it's still an approximately order of magnitude slower, but it is order of magnitude faster than running entirely inside the enclave. That's the sort of the halfway point on the logarithmic scale. We are approximately halfway point on that. And then, so that's what it's showing you. This is approximately 10x. All right. So we said, oh well, this is all no. It's all sort of fluffy, and it's not clear how much actual guarantees we provide. And so we designed a system called DarKnight, which is a theoretically robust privacy mechanism for trusted execution environments. And in this approach, we guarantee zero leakage. So it's cryptographically zero leakage that actually occurs in the system. So for those of you who are more theoretically oriented, you will feel more comfortable knowing that if you use this approach, there will be no information leakage from a cryptographic standpoint. So what is all of this other than the pretty picture? So this is, take a look at this. So the basic principle is basically the same. We can offload computations that are very intensive, linear operations intensive to the GPUs. And we can utilize the trusted execution environments or enclaves for nonlinear operations and for basically doing something called encoding and decoding. And I'm going to explain the encoding and decoding process in more detail in the next few slides. So this is basically what we call DarKnight. I forget it appeared maybe a year ago. If you want to know more details, I think Micro maybe 2020 or 2021. So here are the 8 steps in DarKnight. Clients have a set of information, let's say inputs, and this is again, it could be inference, could be training, but for now, let's just make it simple to look at inference. A bunch of information that they have, they're going to create an enclave in the cloud, and then they create a private key, private public key with the enclave, and then they encrypt all their inputs using that key, and then they send it. In second step is they send it to the enclave, and the enclave will now receive the information, and then it has the public-private key mechanism to decrypt the information within the enclave. So the network itself could be untrusted, but it's okay. We will send the information in a trusted manner. Then in the third step, which is where all the DarKnight's magic happens, there is a linear encoding of all the inputs. Inputs basically are the collection of images that I get. I'm going to linearly encode the inputs within the SGX using what is called the DarKnight's encoding scheme. So we're going to encode those inputs. And by encoding, what we are going to say is that the encoded output, after we finish this encoding, has zero mutual information with respect to the input. That's how we prove that it's cryptographically no information leakage in this system. Okay, so we now do a encoding and we send the encoded data back to the GPUs. The GPUs now receive the data in an encoded format and it looks completely like random garbage from a GPU standpoint. And the GPUs perform linear operations using weights. And again, because it's a model that is publicly known, we assume weights are known for this particular work. But as I said, we can train also. But they compute linear operations using W, which is the mates of the model. And they return the results of the data back to the SGX. And SGX, which is the enclave, is going to decode the results such that it can, because the way it has encoded it, it will make itself easy for you to decode those results after you finish the linear operations. That's what it is going to do. And once it is decoding is done within the SGX, it can perform any nonlinear operations entirely inside the enclave. So the enclave will only do nonlinear operations, and then the process repeats. Right? Okay, so let's take a look at some simple examples to really figure out what is exactly the encoding and decoding process looks like. So here are my 4 input images. That's my batch size for the purpose of this discussion. And these are the 4 input images, X1, X2, X3, X4. And let's say that we have 5 GPUs in the system that we want to use. Right? And so that's the given values for us. And so we have 4 images and 5 GPUs, and we're going to use all of them to actually achieve the DarKnight's goals that we're going to discuss. And then we're going to generate a selection of alpha ij's, which are random scalar variables, and R, which is a uniform random vector, entirely within the enclave. So these random numbers are not visible to anybody outside of the enclave. So these are actually secrets that you hold inside the enclave. Okay? And so now let's see what we're going to do. What we're going to do is the following. You're going to take your inputs, 4 inputs, and we are going to linearly combine them by weighting them with lambda 1 x1, lambda 1 2 x2, lambda 1 3, sorry, not lambda, alpha 1 3 x3, and all the stuff, and finally alpha 1 5 r. So you now combine these 4 images with a random noise and then scale all of them, you get a value which we call x1 prime. For the purpose of this discussion, we call that x1 prime, which is then delivered to the GPU. In this case, it's going to send to the GPU 1. Same thing we're going to do with now a different collection of random vectors, alpha 2 1, 2 2, 2 3, 2 4, and 2 5. And I will do this repeatedly for all the 5 inputs, all the 5 times, basically for this information. And now I got x1 prime, x2 prime, x3 prime, x4, and x5 prime. This is the 5 outputs that I got. And as you can see, each of these has 0 mutual information with respect to the input that we have, because alphas are random, and the value of R that we have generated will also randomize the entire input data set. That's what we're going to do. And all these 5 computations are run at different 5 GPUs in this case. Everybody with me first? It's a simple math, right? High school. All right. And so once we finish that, so this is the data encoding process in math format. X is the input, and x1, x2, x3, x4, and R are the input data that we have, and we have a secret random scalars, which is alpha ij's, and that's going to be presented as a matrix A, and we are going to essentially encode it by using X A transpose, right? That's what previously what we just did. And then linear operations are now performed on those transpose, on those X prime values. And so now the GPU is going to do WX prime, WX1 prime, X2 prime, X3 prime, X4 prime. And so it will produce what is called the Y prime. That's what the output is. What is Y prime with respect to the original inputs? It can be treated as W times X times A transpose. You're with me? Everybody with me? And all I need to do to get my value of WX is what? Multiply it with A transpose inverse, and then I'm done. Right? And so I take this value that is WX A transpose, and then I will basically, and because A is secret, right? This is a secret. And that secret is inside the enclave, so I can actually create my own inversion of the matrix inside the enclave itself. I create an inversion of the matrix inside the enclave, and then I can recompute the WX by simply multiplying the WX prime with A transpose inversion. That's exactly what I do, and this is the result that we are interested in generating. And now we got your WX. And then at this point in time, you want to do ReLUs, nonlinear, any kind of nonlinear operations. We can perform all those nonlinear operations inside the enclave on open data, but it's private because it's inside the enclave. Right? And once it is done, now you get a new activation values, which you can then do the same process repeatedly multiple times, right? For layer after layer after layer. Anytime there's a linear operation, set it to the GPU, nonlinear operations, bring it into the enclave, and then you kind of do this repeatedly back and forth until your entire 152 layers of the ResNet is actually done.
The A matrix can be same across.
So the A matrix could be same for performance reasons, but for actually cryptographic reasons, it has to be different, so that you actually cannot like the reason is you don't reuse the random value more than once ever, right? That's what cryptographically secure requirements are. But for practical purposes, you can basically get away without having to regenerate A's all the time. And the advantage here is, folks, you already recognize that this A transpose and A transpose inversion are offline. I can generate them months before the system goes online. And I can have a whole collection of them generated, pre-generated, and then ready to roll as soon as my inference or my execution starts. Yes. We store them. So here is the advantage, right? Now we can actually store them. We generate them inside the enclave, but the enclave has limited memory, as I said, and that's a good point. And so I can't just say, oh, I can somehow store them. So what I want to do is I generate those A matrices, and I'm going to store them in an encrypted format in the external DRAM. But the advantage is I know, oh, image 1 is coming. I can actually pre-start the process of fetching the A matrix and do the decompression or the decoding or the decryption, and then perform this operation. So essentially, I will not have enough memory to store these many matrices of A inside of the enclave. So I'm going to have to go back to the DRAM. But that's not on the critical path of my computation. I can actually sort of start fetching while I'm doing the next batch. I can start fetching the next A. Yeah. Good question. I'm going to go in 2 slides right now. Yeah. Yes. Yeah. No. Process can be.
Yeah. Oh yeah. So there are 5 GPUs being used here. And I'm assuming that the more GPUs should be able to do the result of the answer.
Correct.
Right?
Correct.
Seems quite expensive.
Yeah, but think of it this way, though. So it's a good question. Dude, you're using 5 GPUs, which is true. But on the other hand, if I were to think of it from the throughput standpoint, how many additional computations am I actually performing? Only one additional computation in this whole system. So on a computational standpoint, the throughput, it's basically I need a minimum of 5 GPUs, but I get 5 times the throughput of the system itself. So it's not any more expensive. There's a capex cost. There's a capitalization cost at the beginning, but it is generating the same kinds of throughput as 4 GPUs would generate. So it's not substantially expensive.
So the WS costs, right? So that can be really large. So how do you manage it? If it is not, doesn't fit into that.
So as you expect, Arka is asking me questions about the memory system, which is basically when you do WX and it doesn't fit into your memory of 128 megabytes. How do you manage that? So the way we manage in our particular system is we basically take the WX prime and we chunk it. And then we can do essentially tiled, this computation that needs to be done can be done in a tiled fashion. Where we basically pick up the piece, do the tiling operation, store it and encrypt and store it, do this tiled operation, encrypt and store it. It's more expensive if it's really big.
Because it's not only the storing, right? Whenever you are doing it,
Yeah,
you have to do an integrity verification as well.
Correct. You have to do the Merkle-Tree verification as well. Yes.
So does this encoding of data come in some performance cost in terms of accuracy?
Absolutely. So as I said, privacy is not free, right? I mean, anytime you want to do privacy, whether it is differential privacy or any other metrics, there's a certain cost associated with it. And that cost is part of the equation, which I will show you in the results. Huh?
Why can't we get
Is this performance? Is there a performance impact due to the encoding process? Because I'm going to do, the reason is I'm actually doing this operation, which is XA transpose, is a new operation that I have to perform. And he's asking, is this expensive?
So I'm asking, does the end accuracy
Oh, accuracy. I'm sorry, I thought I heard accuracy. So no, accuracy will have no impact. There will be no impact on accuracy in this system at all. Zero change. Okay, so integrity check. You asked the question. Here is what the integrity check looks like. So the question about integrity check is very simple. The question, what is integrity check? How do I know that the GPU produced the right result? Right? That's the question that we have. So you got the results. How do you know it's the right result? In computer systems, particularly in computer architecture, people know dual modular redundancy. Basically, you perform the same computation twice and then you verify it on both sides, right? But here it's actually cheap. You have, if you think of it from a linear algebra standpoint and go back to your high school math, all we are doing is there are 5 equations on 5 unknowns. If I can do 5 equations on 3 unknowns, what do I have? I have a redundancy built into my computation, and I can extract the outputs of the 3 that I wanted in 2 different manners, independent manners. And if there is ever a conflict, I know that there is a problem with one of the GPUs. I don't know which one, but at least I can detect a problem in this system. Make sense? So everybody follow this? So basically what we're going to do is we're now going to take not 4 images. If I don't trust the GPUs to do the work correctly, I will remove 1 image. And then I have 3 images. I create exactly 5 equations on those 3 images. Same way as before. And now instead of having a single R, I will have R1 and R2, 2 separate random analyses. And then I execute on the 5 GPUs. I get the results back. Now, when I do a transpose inversion, I get 2 ways to extract WX. And both ways must be identical, otherwise I have an integrity violation in this system. Yeah. Okay, continue the question.
So, I mean, just making this up, but if I was to find a way to extract like whatever lives in the memory of these two GPUs.
Oh, so you're talking about like how do you attack me, right? Like basically, that's perfectly a valid question. The way you attack me is by colluding, right? Like you have 2 GPUs that collude, and then they extract the randomness out of the collusion. Yeah. So I have a solution for that. The colluding GPUs can also be solved provided you can limit the amount of collusion in the system a priori, right? Because remember this redundancy that I built into the system can also be used to deal with adding additional noise into the system. So I can either choose to do additional redundancy, or I can choose to do collusion protection. Either way. And so if I can say that 2 GPUs can collude, I add additional noise to the system so that when 2 GPUs collude, they still cannot actually extract the original information. Exactly the same process. But I mean, of course, you can ask me the harder question: what happens if all the GPUs collude? Raise your hands and say nothing you can do, right? And so there's a limit to how much you can protect against. And so, and I mean, this is another problem too, right? How do you make sure that these 5 GPUs don't interact with each other? There are different ways of actually solving these issues. We don't need to necessarily go into that. Yes.
We learned that we need to inverse of a matrix.
Yes.
We have learned in different subjects that computing the inverse of a matrix is the most
expensive process. Yes, absolutely. That's the reason why I mentioned that A transpose and A transpose inverse can be computed outside of the critical path. In other words, this is A transpose and A transpose inverse are unrelated to the input, right? They are actually just standard random scalar variables. So I can select the random variables if I wanted to in such a way that the rank of the matrix is selected in such a way that the inversion can be computed very quickly. But this is also not part of my critical path. I can do it, let's say, a year before my actual deployment of the system, and I store thousands and thousands of matrices in memory. Huh? That's it have to be one. True. That's why I'm saying that it's in a way. What I'm saying is that this is certainly expensive to do this inversion computations, but it is not on the path of what I need to do.
So this is all local, right? This is only on one machine, I would say. So, I mean, just two questions. So basically, can we not do this spatially, just do it on different GPUs at different locations and make it more foolproof? That is one question. And can we not merge GPU into TE?
Let me answer the easy question. The TE GPU merging happened already. So it's called the Hopper architecture. So GPU Hopper, which is a newest of the GPU design that was released, I believe, maybe 3 to 6 months ago. But we have been trying to get access to it. NVIDIA just released it. It's called H100. They allow you to do an enclave inside the GPU in itself. Right? It's the most recent enhancement for the GPU architecture. And then the first question that you asked, which is, can it actually be fully distributed and you have a distributed set of enclaves? It's possible. It's very easy to extend it in a distributed system. That's not that difficult. But it's just to make sure that your communication panels are always encrypted in that case. That's the only requirement that you have.
I mean, you can randomly spatially distribute it, so make it more difficult.
Yeah, but the problem with cryptography people is they are not happy if you say is fuzzily correct. You have to prove mathematically that there is no information leakage. And for that purpose, when you say you can arrange it in a different manner, it's not enough. You have to show that this arrangement has to be mathematically correctly done. Otherwise, it's not going to be. You might improve it from a practical standpoint, but it's of no consequence in reality. Yeah. Come back whenever Professor Govind is going to arrange the talk on MPC, and I'll tell you why MPC is another interesting domain. Maybe I can continue for those of you who are really interested. I have the slides already, so I can. So, but that is it's a different paradigm. It's a completely different paradigm, but it has its own costs. Particularly when you do MPC paradigm, when you have to do, for example, Beaver triple assisted multiplications, the communication cost can be overwhelmingly large. All right, folks, everybody okay with me? Nobody is lost, still stringing you along? All right, so with that, these are the experimental results. We implemented this on Coffee Lake, which is an Intel processor with SGX support. We used 5 NVIDIA GeForce GTX 1080 Ti's, and we had a 40 gigabits per second infinity band network switch connecting the TEs with all the GPUs. And we implemented BGG16, ResNet 50, and MobileNet V2 as the 3 different kinds of models for this particular implementation. And here is what the execution looks like. On the right-hand side, spelling mistake, baseline, and then here is the DarKnight splits, how the computation gets split. So you can see in linear operations consist of the maximum amount of time. 84% of the time in the baseline is spent on linear operations, which is the matrix operations. In our system, the DarKnight, linear operations are very small, 0.04%. Why? It's because nonlinear operations, encoding and decoding costs become much, much higher. And so this doesn't show that the numbers are the same, right? It doesn't show the execution latency. All it says is that if I take the pi, but the pi is actually much bigger here, right? We're running at a much slower pace. In the bigger pi, a small part of it is only spent on linear operations. Large parts are spent on the encoding as well as the nonlinear operations associated with the system. So, but the pi itself is actually shown here. So let's just take a look at it. So if you look at the total cost of the system, the execution of, let's say, MobileNet or ResNet or BGG, you approximately get around 11x speed up with the about 6x speed up with the DarKnight approach. Compared to what? Compared to running it entirely on the GPU, on the enclave and protecting the data privacy. Any questions?
Just go back to the previous slide. So here when you say the contributions of different components on DarKnight, you are also talking about both the CPU and the GPU together.
So this is the total execution time, if I remember correctly, which includes the CPU, GPU.
And in the next slide, you said that it is about 6.5x faster with DarKnight, but again, assume that this is from the 100x slowdown. That, right?
Yeah, I mean, so as I said, always this is not zero cost, right? I mean, okay, so that's basically. Do I have an additional 5 minutes to continue? Are you all interested or heading for the doors immediately? Okay, so if you're interested, I wanted to cover one more thing, which is also an interesting use of trusted execution environment, but in a slightly different setting in machine learning, which is the federated execution model. So this is called FedWAT, which is an efficient gradient outlier detection mechanism for Byzantine resilient and privacy preserving federated machine learning. Very, very long title, but that's my student's title. But I'm going to sort of simplify this, and this is I call it FedWAT. And so what is the problem here? So the problem here, now we're going to sort of reset everything what we talked about with respect to the DNNs and the traditional system, and we're going to go into federated machine learning. How many of you have heard of federated machine learning? Some of you. Okay, so federated machine learning is basically very simple. I'm going to go through very briefly. There are multiple users who have data. Let's say a mobile phone has its own images that it has taken, and it is unwilling to share it with the cloud to do a training of the data. So instead of sending the data to the cloud and having it trained, which is what my DarKnight approach was looking at, here's the opposite. Send the model to the clients and then let the clients actually train using their own independent individual subsets of data. And then once they finish training, they generate a gradient, and they send, each client sends their gradient to this gradient accumulation engine in the center called the server, which will then aggregate all of these gradients and generates a new model and propagates it back to the clients. And so this kind of repeats in epoch by epoch basis, where you send the gradients down to the clients do the computations and generate a new gradients, which are then averaged, and then send it back and forth. This is what federated machine learning looks like, right? So this is a one-slide overview of the federated machine learning, and so I will sort of click through this because of the time. So here is the problem. The problem is, people are interested in federated machine learning because the clients are thinking that, oh, I'm training on my own local data and therefore I'm not leaking any information. But when you send the gradients from the client to the server, those gradients actually contain private information about your input system. And there have been model attacks that have been demonstrated that show that by just looking at the gradients, I can reconstruct a lot of the input images that are used in the training of that particular model. And hence, these gradients can actually be problematic in terms of disclosing information to a adversary. So this server, which is aggregating these gradients, can look at those gradients and then say, oh, I know what data you used, which is problematic. Right? And so that's problem one. We don't like that. And so the second problem is the other way around. So I don't trust the server, but the server also doesn't trust me, because I can explicitly and maliciously send gradients that have nothing to do with the model. I can just send an arbitrary collection of random vectors to the machine up and say, so this is my gradient. And the server may actually aggregate those gradients, and then you generally sort of drift the model away from what your original intention of the model is, right? And so this has been shown that the clients, particularly a single malicious client with particularly tuned gradient updates, can drift the model to really wrong places in a way. So the problem is, it's like basically India and China. Nobody trusts each other, right? And so now you have to still do business. That's the problem. And so how do you deal with that issue? We're going to deal with that issue by our favorite engine, right? Because this is my hammer, so everything looks like a nail to me. And so what I'm going to do is now I'm going to take my trusted execution environment and say, hey, I am going to put a trusted execution environment inside the server, and I send the gradients to the enclave to perform the gradient aggregation. This solves one of the problems. What does it solve? It solves the problem that the server cannot see the gradients, because you encrypted the gradients and then you send it to the enclave, and the enclave is actually going to do the gradient averaging. And hence, the server, any hacker in the server cannot see the gradients. So that solves the problem to that extent. But we still haven't solved the second problem. And that problem is, what if this gradient is actually wrong? It's maliciously wrong, right?
And so you also need to figure out how do I actually solve that gradient aggregation, the gradient update problem that could be potentially malicious. And so one way people have talked about, and there are many different approaches, one way people have looked at gradients that are potentially malicious is by using what's called outlier detection. It's a standard outlier detection mechanism where you look at the vectors that are coming from all of you, and they certainly follow certain IID pattern, and then there is one outlier that comes from you and says this is really far off from the gradients. And I'm like, wow, that's potentially problematic, right? And so therefore, when you look at the gradient estimates, from benign users look like this, and a malicious user may look far away from that. How do you detect, or how do you do it computationally? The way you do this computationally is just to pairwise distance. It's like basically look at the Euclidean distance across two vectors, and then you know what that pairwise distance is. So if I have 4 entities, I have to do each pair, right? Every one across everybody else. And so this pairwise distancing computation can be in fact performed inside the enclave, right? But this is what the problem looks like. The execution time for pairwise distance computation for different kinds of models is shown here as a function of the number of clients. And the y-axis here is execution time, not in milliseconds, not in microseconds, but in seconds. Very, very expensive, right? So you send the data to the client computes for a few seconds, sends the data back. You will take 1,000 seconds to actually generate the gradient outlier detection and then send the results back to the client. Not very sustainable, right? Basically, the client is sleeping most of the time. And so we got to figure out how do you make this more efficient. Again, how do you make things more efficient, particularly for pairwise distances? GPUs, exactly, right? This is our second hammer we have. So we're going to use that hammer to try to improve that. But the problem is we don't trust the GPUs either, right? So because then there's no enclave within the GPU, but today there is, but in the olden days they didn't have GPU enclaves. And so I don't want to give these gradients to the GPU in a publicly known or open format. I want to give it in some sort of an encrypted format. And so what are we going to do? Same thing. Take the tree, encrypt or encode your gradients and send the encoded gradients to the GPUs. And so here are my 2 GPUs, which we are interested in running the outlier detection algorithms on. And so the assumption here is the clients can be malicious, GPU accelerators are honest but curious, and communication is encrypted and secure. And so here is a simple illustrative example. It looks a lot like a 2-party computing for those of you who are in the MPC, come from the MPC world. And so clients I and J send their updates to the parameters. And here's what the enclave will do. Very, very simple encoding in this case. It will send GI plus some random I, GI minus some random I to these 2 GPUs. And the second is GJ, which is the gradient from the client J, is again GJ plus RJ and GJ minus RJ to the second 2 GPUs. And again, if you look at it from an encryption standpoint, it basically looks like a one-time pad encryption mechanism. And so the 2 GPUs cannot say anything about GI or GJ given the random addition values that you have generated. And for those of you who are from an MPC world, this kind of looks like an additive noise added to the MPC domain. And so, and then the GPUs compute the partial pairwise distances using that very simple, basically that GI primes and GJ primes are shown on the picture. And then the results are sent back to the GPU, to the SGX stack. And what is the SGX computing? It's essentially computing GI minus GJ squared minus this plus this RI minus RJ squared. That's what is the actual value it has computed. And that's what we have computed. Now, from here, it's very straightforward because the enclave generated this RI and RJs because it has known what those values are. It can actually compute this and it can subtract us. That could be one simple solution to actually get the pairwise distancing inside the enclave. What would be the alternate approach? The alternate approach is actually there's a particular way of generating random numbers where you can generate a sequence of random numbers such that Ri minus Rj will always be constant. And if I can create a constant value, that means that Ri minus Rj squared is a fixed value C. Pairwise distancing is not really, I don't need absolute numbers, right? All I need to do is what is off with respect to other people. I don't need to know that this person is 10 and this person is 8. This could be 108 and 110. Is those still okay? So if this Ri minus Rj squared is a constant C, basically we can see that this is a gradient the delta above that constant is all that matters, and therefore you can still do perfectly the pairwise distance computation and outlier detection using this approach if Ri minus Rj is kept constant. Right? And that's exactly what this is showing. And so this is the system that we built and we implemented in the federated model. Again, a Coffee Lake processor, NVIDIA GTX 1080 Ti. If this machine looks so similar, it's exactly the same one that we used in our previous work. And we implemented both a mobile net and efficient net using this particular approach for training. And here is the improvement in performance that you get compared to running entirely inside the enclave. So this is my baseline, running everything inside the enclave. And here are my 2-party and 6-party computations. Basically, when I say 6-party, it is GPUs. 6 GPUs are participating in my computations. 2-party is 2 people are participating in this. And so you can see there is an order of magnitude improvement in performance on these systems. And so this is the 6-party results. And basically, again, it's a privacy-preserving, Byzantine robust. And again, you can see the paper for all the scalability analysis, collusion, all of the stuff that you folks asked about. So in some sort of concluding thoughts here, basically what I wanted to show you is that privacy will become an ever greater challenge in the society, particularly as ML kind of creeps into your bedrooms, right? Like you don't want your machine learning video cameras. And so there is a lot of information that they're going to extract. And hence you have to solve, so you sort of provide solutions. And the performance can no longer be the only key driver for these applications that are going forward. And hence, private and secure machine learning hardware is useful for accelerating these tasks. And SGX is a great example. The GPU's Hopper architecture is a great example. And so there are all these innovations that are happening in the hardware domain that will make your life very, very easy if you are purely thinking of it from a algorithmic standpoint and from a theoretical standpoint. Talk to one of us, and we can help you make your algorithm run 100x faster, right? And so that's the goal. That's what I wanted to show you, is that for those of you who are sort of drowned in equations and math, which I know nothing about, I'm happy to work and interact with you to make this more efficient by kind of taking advantage of existing hardware capabilities. Thank you. 8 minutes behind. Yeah. So, are there any questions from the Professor Govind is asking me if there are any questions that you have online? I'm happy to answer as well.
Can you hear me?
Vinod, I can hear you. Yes.
Yeah. So thanks. It was a very interesting talk. I was just wondering if you have seen this work called ShadowNet, which actually used very similar ideas as DarKnight, except that they did it on the TE, and I think that the insights were also pretty much similar in the sense of doing linear computations inside and non-linear computations outside, or sorry, the other way around. So if you've seen it, sort of any insights into how DarKnight and this and ShadowNet compare?
So I can't tell you the ShadowNet work directly, but we have compared against something called Slalom, which is a paper published from Stanford on the same basic principles. And the big difference is DarKnight can also, so although I showed only the inference, DarKnight can also do training. It can do backward propagation on a private mode by using enclave and GPU collaborative execution. And to the best of the knowledge, all the papers until the time DarKnight was published focused only on inference, and this was the first paper to actually provide training also in a private environment.
Okay, thank you.
Any other questions, folks? All right, if there are no other questions, thank you so much. Oh, yeah. Oh, so I think the question you're asking is how much do I trust the enclave in itself? Yeah, so there are enclaves are actually quite trusted. The only major leakage of information occurs from side channels. For those of you who are talking from a security perspective, side channels are basically I can tell what kinds of computations are you're generating because the heat in your machine is higher, right? That's the kind of side channel information. But if you ignore side channels, very few attacks actually can sort of peer into the enclave model itself. And it's a fair question, and we make the assumption that their enclaves are pretty good, and if you can get a 10x improvement in your performance, it's worth the exploration. Yeah.
Doesn't it give out additional information about DI and DJ
Certainly. So that's the reason why many times you do GI, if you make RA and RJ constant as I just described, then you do not reuse RA and RJs. But it's okay because you can pre-generate a whole sequence of RI RJs and use them separately for each of those GI and GJs.
But RI minus
you can generate a whole sequences of RI and RJs, and you can pick up any two pairings such that there is a constant value.
The constant value. So these two different pairs will be used for different GI values.
Yeah, they could be used for different GI values. Yes, cryptographically, it is not the same as zero information data. You're correct, because there is a certain amount of cross correlation that you can exploit in that case, and that's the reason why I was suggesting that there are two approaches. One is you recompute RI minus RJ squared offline and subtract it out, or you do a constant. But constant has certain, like if you reuse, there is certain limitations.
Let's say parallel learning, like let's say there are malicious people who are trying to go the gradients the other way as much as possible within the limit. Is there a possible that this affects the accuracy?
So what you're saying is that what if the pairwise distancing does not detect because they're just under the radar, like just below the radar they continue to. It's a weakness of the paper. Basically, we assume that pairwise distancing is how you can outlier. There's an outlier detection mechanism that exists, and we are applying this approach on that. But it is possible for a clever adversary to create those gradient updates such a manner that they below the cutoff mechanism and sort of impact the model.
Is the limit determined empirically the pairwise distance?
Sorry?
The limit value. Is it determined empirically or?
In almost all the papers that as far as I know, Crum, which is one of the most well-known papers, actually uses a threshold cutoff that says that if the pairwise distances, think of them as like how far you are from the neighbor, and then you just do a distribution, and then you cut off and say that this is outside of my trusted domain.
So this is all done in GPU, but is it possible that we do it on tiny kind of things? Because I'm just seeing whether there is any lower bound of energy usage. This is all high energy use kind of thing, right?
Yeah, ML is all about high energy in some sense. Like, I mean, GPU is burned down in the whole house in some sense. But yeah, I mean, there's nothing. So you can see this is an algorithmic approach. There's nothing really. You could use a CPU to do these computations, and you will still run, but maybe a little bit slower. So there is nothing fundamentally limiting you to a particular hardware model. It can be used for.
If you're talking about MCU, right? You're probably better off doing all the computation in the trusted environment. The MCUs are significantly slower compared to your trusted.
Exactly. Yeah.
Okay, if not, let us thank Murali. Just wanted to get a quick feedback. Do we have the next talk within a week's time, or how about you, Murali?
I can do it, but
I just wanted to check with these people since they are here now. If we do it next week, is that still convenient for you? Maybe you can just come up with your hand.
Raise your hands if you want to stay with me for one more.
Yeah. Otherwise, we'll have to take it to January. So I was wondering whether we should do it. It's okay. There are still a good number of people. So we'll try to do it before November 30th, so that we can attend.
I'm surprised that you wanted to listen to me one more time, but I'm glad I heard you. So yeah, so I'll be there'll be an announcement, and it will be. I promised. I think some of you it will be on MPC, multi-party computing, and how to make MPC more efficient.
Okay. On behalf of the department, I would like to present the member to Murali. Thank you.
Thank you. have to stop the recording. Yeah?
I did.